Hello and welcome to today's webinar, the Distributed Battery Part 2. My name is Cody and I'll be your moderator for today. Today's webinar will run for 2¼ hours. We'll try to stick to the breaking points as closely as possible, and we do have a few notes to go through before we begin. Please be sure to be
3¼ hours.
Oh, excuse me, 3¼ hours. Thank you.
Yeah.
Please be sure to be logged on to the webinar through your own individual connection, so that we can accurately prove attendance in the event that Half Moon or you is audited by any licensing board. We also require individual connections so that you can access the quiz at the end of the webinar. The quiz will automatically appear on your screen after I end the webinar today. If you are not able to successfully submit the quiz, you can always access the quiz via the thank you or follow-up email that is sent about 1 hour after the webinar has ended. Certificates will be issued for today's webinar. If you did not successfully submit the quiz after attending the webinar, please be sure to complete the quiz through the thank you or follow-up email. The certificates will be sent via email in PDF form, and if you need your certificates sooner, please reply back to any emails you have received regarding these seminars or call into our office. We will be taking questions throughout today's webinar. If you have a question for Mr. Cromer, you can ask your questions in the questions area of the GoToWebinar panel. Materials for today's webinar were sent via email. If you weren't able to receive the materials, you can access them in the handouts section of the GoToWebinar panel. Once you click on the PDF, the document will open in your default internet browser where you can view, download, or print. And with that, I'll hand it over to Mr. John Ross Cromer, Master Electrician, Mechanical Engineer, and Certified Photovoltaic Installation Professional.
All right, welcome back, everyone. Let's go ahead and dive right in. We were kind of going through this off-grid residential case study, and what I see a lot on residential off-grid is using multiple inverters. It just makes sense to have some redundancy built in so that if one inverter fails, when you're grid connected, no biggie. You just run off the grid and you pay more for your electricity. Off-grid, if one inverter fails, you'll be out of power or just running full-time on your generator until it's fixed. So building in some redundancy is useful. In fact, I haven't come across any major battery inverter that is not designed to be double stacked or triple stacked or quadruple stacked. And that means on these smaller string inverters, they're very scalable up to 100 or 200 kW. And at which point you'll get into more commercial battery inverters. We looked at some different charge controllers, and when you get into charge controllers, there are a variety of advanced features, and I'd say that SMA with Midnight, Midnight is a US company, and SMA was slow to kind of get into the battery market in the United States. But Midnight has a good reputation of having a lot of advanced features. In researching this class, I came across a National Park Service project up in Alaska where they actually have dozens of charge controllers on an off-grid array, and the charge controllers are programmed to rotate in operation so that they are there's more charge controllers than they need, and they're designed to rotate in and out so that they're always kind of being tested but not gonna ever run out of power at this remote site. But we ended up going with Schneider mainly because it was the company that had the most market experience with a 600 volt charge controller. In fact, only Morningstar, and I heard good things about Morningstar as well. I just am not as familiar with them as these other companies. So it was a real simple decision at the end of the day, because we couldn't go with Outback, we couldn't go with SMA. We wanted to have these 600 volt larger circuits up on the rooftop. Although I suppose with SMA we could have done AC coupling and done 600-volt regular inverters with the battery inverter being separate. Let's see. So we, in terms of optimizing design, what I have found in my solar practice is that generally you want to design systems. You have a custom design for every rooftop, and sometimes that means that your inverter is oversized or your inverter is undersized. When I think it's a good design practice to look at the maximum capabilities of your individual components and try and max them out, and then work your way backwards from that. So looking at these charge controllers, originally I thought that they only had 2 inputs. Pulling open the spec sheet, turns out they have 3 inputs. There's a National Electric Code rule that says when you have 3 or more circuits wired in parallel, you have to put in inline fuses. So if we just stuck to 2, in this case, we could just run the solar array directly into the charge controller without fusing the circuits. Not that big of a deal one way or another. But it turned out that these charge controllers have an output of about 4,800 watts each, and with 2 circuits that maximize their output voltage. So each charge controller, we're going with 2 strings into each charge controller. Looking at the terminal blocks is another good point where you can spend all this time on wire sizing and calculating the best wire size for your design. A nice starting point is to go and start by looking at the wire terminal blocks on your individual components and seeing what the largest wire size is that they can actually accept. In solar design, you're often upsizing your cables in order to reduce resistance. Resistance has an even larger impact on batteries than it does on solar. Solar, the more resistance you have, the less efficient your system is, and that means you produce less revenue. So you upsize your cables to make more money. With batteries, particularly if you have more than 1 circuit of battery, if you have different resistances in each circuit and your batteries are being wired in parallel, what that will do is it'll cause the battery with more resistance to degrade faster than the others, and that'll have cascading effects down the line. So I think in all of, especially with off-grid, to look at starting and looking at the terminals and saying, okay, well, my battery terminals, the largest terminal size is 2 watt, and so I'm going to start with 2 watt. There's really no reason not to do less than that. If we're talking about a 7-foot battery cable run, you want to have the least resistance in those cables possible. With solar, you're generally going to be upsizing. You might do your voltage drop calculations and find that you only need number 14 or number 12. Most solar installers are going to upsize to number 10. In this case, the solar charge controllers have landing terminals that could go all the way up to number 8. The problem being is that those MC4 connectors on the back of the solar module are generally only available up to number 10. So you're generally going in number 10 wiring between the charge controllers and the solar array, and then looking at the terminal blocks and kind of maxing out your cable size the rest of the way through your design. And so, when I was talking with Schneider about the batteries, again, there was, I said, well, how many battery circuits can you support? And Schneider said, well, we'll support up to 3 circuits of batteries, but it's generally recommended to be 2. And I've come across battery aficionados who say, actually, if you can just do 1 circuit of batteries, that's the best, because then you don't have to worry about resistance in parallel circuits. The hard part about 3 batteries is, let's say you have, here's battery 1, battery 2, and battery 3, and then you have your inverter on the wall. Your designer is just going to say, okay, well, we're going to wire these 3 batteries in parallel. But generally what's happening is you're actually running the batteries all the way back to the inverter and landing on the inverter itself. And, if you have 3 different strings, this is a very difficult situation to get those circuit links to be exactly the same physically. 2, usually you'll have a battery bank where you might have a shelf, and so you'll have your batteries on the bottom shelf being circuit A and batteries on the top shelf being circuit B, and the wire run is exactly the same. In our case with off-grid, in our design, we didn't build a battery shelf. The batteries themselves already came with a metal enclosure, and we set them on the ground. And so what we had to do is make sure that the battery bank that was further away from the inverter, we started with that wire run back, and then we measured out the other battery wire run and put some slack in it to make sure that it was the same length. Ultimately, we did not go with a 2-volt battery or 6-volt battery. We went with a 12-volt battery, 8 of them. What we ended up needing was around 120 kilowatt-hour battery bank. As you saw yesterday, the client told us that they did not want to have to rely on a generator in order to live off grid. We're still using the generator to protect the batteries and to maintain the batteries, but we designed the system so that it would be large enough that if the generator wasn't there, they could still recover during the winter or particularly wet summer. And so we're looking for a 120 kilowatt-hour battery bank. I need to plug in my laptop here. We ended up going with this 1270 amp hour battery. Again, there's really no penalty for oversizing your battery bank. Your batteries will just last, that percentage longer. And so we kind of overbought our storage. Our batteries, they're designed to last about 12 years, but given that we're protecting them and keeping them in a temperature-controlled environment, they should last much longer than that. But the main thing that we looked at, these batteries are, 10 inches wide, 2 inches long, and 38 inches tall. And then the problem was the batteries weigh 1,000 pounds each. And so we ordered the batteries, and we said, well, we need to specify a lift gate. This is to a direct delivery to a residential job site. And then we get a call from the UPS local distribution shop saying, well, we're trying to deliver your batteries, but the problem is the batteries are stacked 4 batteries to a pallet. And what that meant was that pallet of batteries with 4 of them on it, it meant that the pallet itself weighed 4,000 pounds. And the lift gate from the UPS freight delivery driver was only rated for 3,000 pounds. So they couldn't actually use that lift gate to deliver the batteries. I wish we had caught that ahead of time. We could have told the battery manufacturer to put 3 batteries to a pallet instead of 4. They were trying to save shipping costs by putting it on 2 pallets instead of 3 pallets. It ended up we had to rent a lift that cost about $800 just to offload the batteries, and then we got a battery crane on site. It's just kind of like a mobile hoist to pick the batteries up and move them to where they're going. So sometimes going with what's nice about going with these industrial forklift batteries are that they're tall, so that they're they have the most density, in the sense that instead of having 48 batteries that you have to wire up you only have 8 batteries. And instead of 48 batteries, they have to wire up and then build a case and shelving system. The 8 batteries come with the case kind of integrated into it. So you get a more professional, complete battery when you go for the industrial forklift batteries. But then again, it becomes very difficult to land the batteries on your residential job site. It might be that you have to go with a smaller battery just for transportation issues. But in our case, given that the batteries are going to be lasting for over 10 years, and you know, their batteries are going into a control room in the garage. It's not like they're going into the basement of a home or whatever. You know, it's a little bit of hassle. It was a little bit of hassle to kind of wrestle the batteries into place, but that's only one day on the job site for something that's going to last for, you know, the years to come. There are rules in code pertaining to the layout of electrical equipment. In general, you're not supposed to combine electrical spaces with other work scopes like plumbing or air conditioning. And by spaces, I mean the square foot distance. So you can have rooms that have multiple scopes in them, but you know, if you mount an electrical box on a wall, you're not supposed to run plumbing right across that same space. And so one issue that we kind of ran into was that you know, not only do you have to have the batteries, they have to be accessible so that you can maintain them. You know, with lead acid batteries, you're watering them and you're checking the electrolytic levels. And so if you can't access 3 out of the 4 sides of the battery, you know, that's not an accessible battery. Now, we bought a watering kit so that, you know, we don't need to water the batteries except at one point. There's height requirements and width requirements, but the main kind of odd thing is the depth of the battery. So when you're doing a solar array, it's generally pretty easy to locate the inverter. You're either, you know, if this is our building and our electric service is coming into the building, generally you'll either put the inverter on the outside on the wall or on the inside of the wall right next to your electrical unit. But when we're talking about battery banks that are, you know, just our inverter system itself with with 2 inverters because it's redundant, plus our charge controllers, you know, that's an 8-foot wide inverter, where normally at the residential level you're only dealing with a 3-foot wide inverter. And then you add in the additional spacing of the batteries, and then you realize you really can't have the inverter located, you know, over at one section and then the batteries over at another section, because you want to reduce that wire run between the batteries and the inverters as much as possible. You really want your batteries to be right next to your inverter. And so the spacing requirements of the system can become an issue. So here was our room, and you know, what we see is this wall right here was only 15 feet long. And so you can look at a 15-foot completely empty wall in a control room, and you might think, well, that's plenty of space for all of your solar equipment. The solar installer might say the same thing. But by the time we go and we put in an 8-foot battery bank and a 7-foot inverter system, all of a sudden, you know, that's not enough space in the wall for our system. We have to have, you know, we might have gotten our height requirement all right, and based on the interpretations of the width of working space, that might have been okay. Depending on the battery selection and equipment selection, it wouldn't be okay if our batteries were right in the corner of this room, because again, this side of the battery bank needs to be accessible if it's a battery that requires maintenance, like a lead acid battery. And so to kind of redesign this battery room and keep it code compliant, you know, we ended up removing this door and just having one door to the room, and then shifting the batteries over and putting the inverter system along this line and kind of catty cornering the the wire run between the two. So it can just surprise you at how much space the batteries actually do take up. These are gel batteries, which is why they're on their side rather than being upright. You know, rather than catty cornering our batteries with our equipment, you know, you could say, well, can't you overlap to some extent? And like these charge controllers really aren't there. They don't have any buttons. You know, you're not ever going to touch them. So if we wanted to keep everything on that wall, could you overlap? And one issue to keep in mind is that with National Electric Code, generally you don't run into this, but there's a rule that says the front of this inverter, which is about a 9-inch depth, cannot stick out more than 6 inches to the other next electrical box. So we have two electrical components, and that's if they're stacked within the same plane. So that would apply to this section right here, where we have one electrical component sticking 9 inches off of the wall, and then a second electrical component sticking 38 inches off of the wall. So we weren't able to overlap them because that would have been a code violation as well. So, you know, really this inverter wall, originally the architect had said, well, we're going to have the batteries here and then the batteries here and the inverters here. Getting further into the design, we said, well, these have to be much closer together. And that might be a reason to do AC coupling as well, is so that you can have your solar inverter on one side of the facility and your battery inverter with the batteries on another side of the facility. Sometimes just your design constraints are going to make it so that DC coupling is not possible. So what we see in these pictures, and these are actually taken off the manufacturing website, is potentially these batteries are not accessible for service and maintenance. You know, they have the watering kit installed, but you still can't measure the battery electrolyte level without kind of getting into them. And then on this one, you see the depth issue. So, you know, just kind of keep in mind that if you are going with lead acid type batteries, you really want all sides of the battery to be, or at least 3 of the 4 sides of the battery to be accessible. So one issue with lithium-ion batteries is they're actually a little bit difficult to procure, especially, you know, like the Tesla Powerwall is all but impossible to actually purchase. You have to get on a wait list. So if you really want to move forward with your battery project today and you're doing residential, it's going to be a little more difficult to avoid lead acid. We have 2 options here. We're looking at 120 kilowatt hour flooded lead acid. Our average depth of discharge, and it's less in the spring and fall and more in the summer and the winter, but our average depth of discharge is 30%. It's going to cost us $25,000, rated for 4,100 cycles, although we did get at the last minute a bid from another manufacturer, Hawker, and their lead acid industrial battery was rated up to 4,800 cycles. So that moved our battery life up to about 15 years. But the short of it is that we're dealing with 122 kilowatt hour battery, flooded lead acid battery bank with a levelized cost of energy of about 16 cents a kilowatt hour, or we had this nickel iron battery with a levelized cost of energy of about 8 cents a kilowatt hour with substantially more cycles. So this is a 10-year battery, and this is a 30-year battery, and the 30-year battery costs twice as much as the 10-year battery. And so you could say, well, yeah, the nickel iron is the more cost-effective solution. That said, the client, you know, it became a budget issue. And what prompted him to go off grid to begin with was he got a $20,000 quote from his utility to bring the power lines out to where he wanted to build on his property. And so he thought, well, I'm doing solar anyway. What if I put 20 grand into a battery bank and see where it's at? So he was more thinking in line of a smaller budget rather than a larger budget, and that's fine. The thing about going with a 30-year battery, there's a few downsides. One is you have to buy all 30 years worth of storage up front. And so it might be that it does have a lower levelized cost, but the capital cost up front is just too great. Also, the cost of batteries are plummeting. And while cheap lithium ion is not on the market today, it should be on the market 10 or 15 years from now. And so he says, I'm not going to put all of my eggs in one basket. I'm going to go with the cheaper lead acid today, and then we'll go with rather than the more expensive option that had a lower levelized cost of energy. And so that's something that you can consider across all aspects of projects, rather than not just off-grid residential or luxury off-grid residential, but if you're trying to do a small off-grid project, or even just dipping your toe into commercial load leveling, you can use lead acid for small off-grid and for commercial load leveling. It's just that the batteries will brick faster. If you go and use golf cart batteries instead of forklift batteries, it might be that the batteries last 4 years instead of 11 years, but they're also substantially cheaper. And so if you go from an approach of, well, let's install all of the infrastructure, but put a really cheap battery in line and we'll run it into the ground, and then 4 or 5 years from now swap it out with the latest and greatest battery technology, that's not a bad strategy to consider, particularly if you're budget constrained. It might be that you do a 8 kilowatt commercial battery system today, even though the commercial facility load might be 1 megawatt, just to demonstrate the savings and kind of, dip your toe into the pool before you dive in. Now, some kind of different things about this off-grid project that aren't exactly related to batteries. One is we had a standing seam metal rooftop. And when I do standing seam metal rooftops, what I'm used to is I actually do a lot of corrugated metal rooftops. And so there's a metal roofing company that specializes in solar attachments for metal rooftops. And in our solar class, we go and we look at these attachments. You can say, okay, well, with standing seam, you usually get a little clip like this that just clips around the standing seam, and that's sold to the customer under the no, we don't need to penetrate into the metal rooftop. We can just clip to the roof. Well, what about the cables that come out of the solar array? If you don't go into the roof, then you have to go across the roof. And I think running your solar cables across the roof looks bad. Not always, but I like to hide my combiner boxes and stuff underneath the array and go into the roof deck rather than across the roof. So you might need to penetrate the roof anyway. But also, when I do metal rooftops, you don't always have that standing seam. And so we're looking at different, so in another class, we kind of highlight this corrugated metal roofing bracket where you're actually going into the metal roof, kind of with the context of, these solar attachments are designed to be penetrating into the rooftop in a waterproof manner, that solar is not the only thing that pokes a hole in the rooftop. And, I look at, this is the same kind of fastener that, or bolt. It's the same kind of bolt you know, industry calls them fasteners, that's used to attach the metal roofing panel to the roofing system anyway. So I like, you know, penetrating into the roof and having a nice, secure attachment. The problem with these standing seam clips is that instead of going into the roof truss, you're staying on top, and the weak point doesn't become how the module connects to the roof. It's how that metal roofing panel connects to the truss. And so generally when you use these standing seam metal roof systems, you have to go onto every single standing seam, which might be 16 inches apart. Whereas in normal solar, when you're directly attaching to the rafter, you're generally going 4 foot on center. And so the difference between doing a penetration every 4 feet versus an attachment every 16 inches, you know, that's easy to skip over if you're a solar installer who's not really evaluating the structural side of the project. Now, something that is kind of unique about this clip is normally you're going to have solar rail where the clips, and you can see here the clips are directly attached to the solar module itself. You know, normally these clips, you would have a little L-foot attachment. So you have a little bracket that pops up with a slotted hole in it, and then you get rail that runs across the roof that attaches to these slotted holes, and then the modules get clamped down onto the rail. Well, what we can see is we've removed the rail from the equation. And when you're removing the rail, you might think, well, there's some cost savings there because you're getting rid of the rail. Well, there's a couple of things that installers don't like about these railless systems. One is the L-foot clip. That kind of looks like, so here's your L-foot clip. The rail bolt hole is actually a slot, and that allows you to kind of level the rail up and down. You know, roof surface is not completely flat. It'll undulate a little bit, and so when you bolt what is a rigid rectangle onto an undulating surface, it's gonna try and torque out of square. And it can get, if you're not squaring your racking system after you attach it to the rooftop, then when it comes time to bolt down the modules, the modules can start kind of climbing up the rail, and visually it looks ugly. So particularly on residential racking systems, installers take a lot of pride in how their solar arrays look from the ground, and that's important. But then when you get onto an older rooftop, and solar is often a retrofit on older rooftops, these railless systems cause those squaring and alignment issues to be even greater. So the solar installer will say, well, you know, I don't like railless systems because they're more difficult to install. You don't have as much space between the roof deck and the modules, so your cable management becomes more complicated. The modules get out of square because you're not able to level the L-foot. You know, one reason why I ended up not really liking the railless system is that it really didn't save us any money. Now, I thought the going with railless racking was going to save us a ton of money. I thought it would reduce our racking costs by half or more. But the thing is, these attachments cost money as well. And so instead of going 4 foot on center, you know, we're buying 4 times as many attachments as we normally do. And these attachments are $10 a piece. And so, you know, what would have been really expensive is if on a standing seam metal rooftop, we had put an attachment on every seam and then did the rail on top of that. That would have been unnecessary cost. Structurally, it would have also been unnecessary weight. And on a standing seam metal roof in particular, that extra weight when you get uplift force from a 3-second wind burst, is going to put even more force on that metal roofing panel. And so while I absolutely agree with solar installers who, when they're on an older shingle rooftop, they really don't like railless racking systems because of installation and alignment issues, I actually, at the end of the day, on a standing seam metal roof, almost feel like you have to go with a railless system because it's so much better structurally for the rooftop. You're already on a metal roofing panel that was not designed for the additional weight of that solar array being on top of it. Wind can get underneath the solar array and cause that weight to be an issue. And so with a railless system, you're lowering the module closer to the roof deck, so you have less force. You're getting rid of the rails, so you have less weight. You know, it's a pain in the butt to go and install these clips along every single seam, especially if you go with the cheaper kind of metal roofing system. Our metal standing seam metal rooftop actually was kind of a triangular crimp, and so we had to take a crimp tool or like a clamping wrench and actually kind of push some of this triangular standing seam into a straighter, you know, we had to kind of push it into a straighter triangle so that our clip would actually fit onto it. And so we had 8 rows of modules. You know, the rooftop going across the roof was, you know, there's about 10 modules each of about 5 feet per module. So we're about going 50 feet. And so every 16 inches, you know, that's a lot of time on the roof, bending over, crimping, and putting the rail on. We also ran into another problem with the racking system in that this standing seam bracket is designed to accommodate a wide variety of modules. Now, module frames are generally 30 to 35 millimeters. And if you get a more robust module frame with a little bit better wind rating, it might be 40 millimeters. But there are some modules that go all the way up to 60 millimeters. And normally when you're buying these brackets, the manufacturer, your distributor will ask you which module you're using so that you get the right kind of clamp. Now, the problem with these brackets being designed for all the way up to 60 millimeters, and S5 has since announced that they're redesigning this, but the problem was these bolts were tall enough to accommodate a module frame that was almost twice as thick as our module frame. And so we have all these bolts sticking up throughout our system. And in addition to having to install each clip before we got up on the rooftop, we actually had to go and saw the bolts down so that aesthetically the system worked. Another complication we had is that, as you can see, this clip is silver. Now, I like all black modules. So on this system, we're going with an all black module and a black module frame. And actually, you know, I like black for a few reasons. You know, black never goes out of style. So it just looks good. 30 years from now, it's still going to look good. You know, this system is providing all the power that the house possibly needs. So there's really no reason for this solar array ever to be considered obsolete or old, because it looks good and it provides all the power that the client needs. But if we're going with an all black module and a black frame, and then we put these silver clips on it, that's just going to destroy the aesthetic value of why we're going with all black to begin with. So we had to order these clips and then send them to a metal shop to get them anodized black. And then we had to cut the bolts down and put on a lot more clips than what we're normally used to. A little bit more work on the front end, but the end result was a really nice looking array. So finally, the last kind of bugger is, well, how are we going to transition on this metal roof? How are we going to transition the wires from the array into our control room? And again, I'm not a fan of external conduit runs. If we had done an external conduit run, well, our batteries and our inverter are inside the building anyway. So what? We're going to run our conduit across the roof and then loop over the edge of the building and then go into the building wall. You know, that's going to look really ugly for one. For another, it's just additional length of your cables that doesn't need to be there. Additionally, it's better to have stuff inside the building rather than outside of the building. You have cooler temperatures, less exposure to the elements, less exposure to critters. You know, there's a number of reasons to be inside of a building rather than outside of a building. A number of advantages. And so on a previous project, actually Half Moon's project, you know, what we did with their corrugated metal roof is we said, okay, well, remember that solar is not the only thing that pokes a hole in the roof. How do, you know, other on a metal rooftop, on a corrugated metal roof, how does the plumbing vent get out of the building? And it turns out, well, you drill a hole in the roof and you stub up some conduit, and then you get a pipe boot that flashes around the penetration. And so on a different project site, we penetrated the metal roof, we put in a pipe boot, and we mounted the junction box and hid it underneath the solar array. And that worked out all right. We did have one leak because the installation crew failed to seal the inside of the block. And what happens when water runs down this, you know, it didn't get into the pipe boot, but the water actually climbed up the pipe boot and started getting into where the conduit and the box intercepted. So we had to take the module off, open the box back, and apply some sealant around that penetration of where the conduit and the box hit. So I didn't really like that solution. It was, you know, could we improve it? Well, so then you get to a metal roof, and on a metal roof, you get to the roof cap, and in this one, this is showing a sealed roof cap. Ours was actually, my experience and what we did is had a vented roof cap where this ridge is open. And so he said, okay, well, if we have this Z-purlin here, can we drill a hole into the Z-purlin and run our cables up through the Z-purlin and then into the rooftop? And what that meant is we have a 1-inch dimension in this Z-purlin, and we drilled and it was really close because what I thought was, okay, well, we can drill a 3/4 inch hole into the Z-purlin and be all right. Well, the problem with a 3/4 inch hole is the fitting that goes around the hole was right at 1 inch. So we were barely, if we had, you know, it might have been better to do more penetrations with a 1/2 inch hole rather than fewer penetrations with 3/4 inch hole. But essentially, we put the fitting around that Z-purlin and then connected the Z-purlins to the grounding system. There are temperature considerations when you get this close to the roof deck. You have to upsize your wire gauge. That was the only real concern. With AC, you also have concern about these Z-purlin when you penetrate metal, having some inductive heating occurring, but none of that was an issue. You know, in more professional metal roofing systems, you have this roof hood that could cover a penetration, but that costs money as well. Let me pull up some pictures to show you the final product. So here's what that looked like. And so we have 4 charge controllers, and with 2 circuits each, we don't have to do inline fuses. As far as rapid shutdown goes, well, we actually didn't do rapid shutdown on this project. This is in rural Mississippi. I've even done megawatt projects that don't require an electrical permit. But to make this array rapid shutdown compliant, we would either locate a rapid shutdown box on this side right before going in, and it wouldn't be a combiner box. We just take our circuits coming in, put them into a box, and have it be a rapid shutdown box. Or you could locate within 1 foot of the array, which is the hard part. You could locate the rapid shutdown combiner box right underneath the roof deck inside the building, where these cables are going into the building. But what you can see here is that we have 4 charge controllers. We have 4 circuits. These circuits are going right down to the charge controller. A few things to keep a note. One, DC wiring must be enclosed within a metal raceway. And so this is not just flex conduit, this is metallic flex conduit. So it has a little bit of a metal lining inside here. And so we have metal bushings because it's DC. We have a metal flex conduit because it's DC. So you can this made our this basically meant that our wires came out of the array and went directly into the interior of the building. Looking at our project budget, we said, okay, well, we're going to aim for around a 20 to 24 kilowatt array. We're going to be buying by the pallet. So whatever the pallet quantity comes out to, that's how we'll decide it. So, if it's the difference between buying 24 modules and paying about pallet busting fee versus buying 25 modules and not breaking up the pallet, your distributors get better shipping pricing when they don't have to bust up a pallet. And so, I find that it's generally you can just buy by the pallet and get similar pricing to buying less than a pallet. So might as well buy a few extra modules, then we don't have to worry so much about the warranty. And so we went bargain hunting. We're very patient with our modules, and eventually we found all black monosilicon modules for 50 cents a watt, just by being patient. And so our modules were actually, this is an $80,000 project budget. The solar modules were not the major cost component of that. The batteries were. Our racking system came out to be about $4,000. This is the hard cost of our Schneider system. That's the distribution panel, the charge controllers, the inverters, and all the accessories. At $13,700 for a 20 kilowatt system, this does include some additional balance of system material, but you really do need this balance of system material for a larger battery inverter system. Your inverter related project costs, 20 kilowatts, $13,600. Our inverter budget came out to be over 50 cents per watt. In fact, it was more like 60 cents per watt. Now, normally a high-end inverter budget at the residential level wouldn't be more than 30 cents a watt, and on the low end, it might even be 15 cents a watt. And so we're spending a good 2 or 3 times as much on a battery inverter system as far as the inverter budget goes than we would on a batteryless system. And of course, that's because, mainly the fundamental cost is that batteryless inverters are one way. They go from the solar array out. Battery inverters are two-way. Either you're buying a charge controller and a two-way battery inverter, or you're buying a one-way inverter and a two-way battery inverter. So you're just buying more stuff. You're buying more capability. Balance of system material was pretty cheap. We spent about 25 grand on our battery. And so at the end of the day, this off-grid system is costing the client. The one item that's not included on this list is the generator. So at the end of the day, it's going to cost them about $80,000 to go off grid. Looking at his payback, he gets that 30% federal tax credit. And then on top of that, the utility was going to charge him $18,000 to bring power out to the property. And so between the avoided cost savings of avoiding that interconnection and then taking the 30% off from the tax credit, that means he has to recoup about $35,000 to get his payback. Now, he's going to save between his meter fees and his electric usage about $3,000 a year. And so he's going to get an 11-year payback on his system, which is pretty good. This is for a self-installed system, so the labor isn't in there, but on a 20 kilowatt project, your labor budgets can be 20 cents a watt. So he's going to get a decent payback on this system, but that's only because he's saving $18,000 in avoided costs. If he was twice as far out and his quote was $40,000 instead of 20, he could, for the grid expansion, he would be making almost an instant payback. But the problem is, somewhere between year 12 and year 15, he will have to buy a whole new $25,000 battery bank. And so he really isn't saving any money at all by going off grid. He makes a 12-year payback. He has to buy a whole new battery bank at some point. And so, he's getting he'll get his money back, but not much more than that. He's not buying the off-grid array necessarily for economic reasons. He's just concerned that, is he getting his money back? Yeah. Is he never going to get an electric bill again? Yeah. And that's what's important to him. Maybe when it comes time to replace these batteries at year 11, 12, or 15, the cost of the batteries will be lower. Now, one thing that we evaluated was, well, what if we bit the bullet and we paid the $18,000 for the grid interconnection cost, and instead of doing an oversized system that you would have for an off-grid, we do a more reasonable size system that might net meter out his electric bill, or do something slightly less than that, because in Mississippi they don't have great net metering policies. And we could say, okay, and we'll still get you a battery inverter rather than a battery-less inverter, and that might not be, and so we'll still get you a small battery bank, maybe 10 kilowatt hours instead of 120. Actually, we couldn't do 10 kilowatt hours because this particular battery has a minimum 20 kilowatt hour battery bank size. So that's a little bit, but like the Tesla Powerwall would fit that example. I mean, say we're going to get you a battery inverter, a small battery bank, and just do a smaller project and go ahead and bite the bullet and spend the $18,000 on the grid interconnection fee. And so to have a grid connected solar array for him on his particular job site and still have the ability to have backup power from his solar array, so that if there's a disaster, he's still secure, that would have cost him much less money. And then after you apply the tax credit, I think this should be I think there's a typo here. I think this is a 58, and the tax credit would be $15,000, or maybe I have to go and look at that. So let me just do this really quick. So if he's going to spend $58,000 You know, the tax credit at 30% is going to be about 18,000. So, you know, 58 minus 18 is going to bring you down to 40,000. And so if he's spending $40,000 on his solar array and he's saving at $2,500 a year, and that's because he's still, you know, when you're grid connected, you're paying meter fees. You're not saving at the meter fee rate. Meter fees out in my neck of the woods are actually quite expensive. We're talking about $30 a month. So that's still going to be a pretty big payback. $40,000 divided by 2.5. You know, you're looking at for him, it would have been around a 16-year payback. But then again, he doesn't have to swap out. You know, he's not using his batteries on a daily basis, so he's not going to have to replace his batteries at year 12, year 15. It would, over the long haul, for this customer, it would have been more cost effective for him to pay the grid interconnection costs, even though they were so large, and interconnect to the grid. And so, you know, what I would say is, even so, you know, even when we pointed it out to him that, hey, you know, we could save you some money by still doing the grid interconnection, he had other reasons to go off grid. One is, this is his retirement house. It's being built on like the only hilltop in Mississippi, and he didn't want to bring it and to go from the power lines that cross his property out to where he wants to build. He would have to cross over a creek and destroy his scenery. And so there's some, you know, his property remains beautiful by staying off grid. That has some value to him. Another issue is that he was mad at his electric cooperative over their solar policies. You know, so he wanted, the utility had a program for large project development. And one of the original uses for his property is he thought, well, maybe I'll put a large solar farm on it. And so we did the application for and this really wasn't even that large. It was a 350 kilowatt, and the utility would be buying the electricity at 6 cents a kilowatt hour, which is about half the retail price of electricity. And to qualify the system for the utility program, it also had to be a community solar project. So here he was willing to be an investor in a 6 cent a kilowatt hour, which would have reduced the price of electricity in the area, solar array, and he was willing to run and administer a community solar platform on it so that other people could buy into the array too. We dropped off the application at the electrical cooperative, who was a participant in this utility program, and the cooperative essentially told them that they didn't have a lawyer on staff to review the application, and they had other priorities. So even though they were participating in the utility program, they weren't going to evaluate his application. And that ticked him off. And so then it gets time to the point where he's building his house, and the difference between going off grid, where, you know, if we actually are being honest and incorporating the cost of the battery replacement, would get him a 20-year payback versus paying the interconnection costs, and he'd be getting a quicker payback. And he says, well, I don't care. You know, I'd rather spend more money to go off grid than to remain grid connected. And so I think that is, you know, one thing that utility program developers should be thinking about is that solar customers are willing to pay for the grid connection. There is value in having a grid connection, even if it's $30 a month and you're not buying any electricity. Just having the grid connection there as a backup offers value. But then again, many solar customers have deep pockets, and if they feel like they're being discriminated against unfairly, if they're being asked to put in more investment to build out a solar array and they feel like they're up against some anti-solar policy, it doesn't have to be an economic decision to go off grid. It just has to be close. It might be that they would get a better quality of life having that grid connection there as a backup. But they say, well, that's not enough for me to get out of the system. And so, you do have a lot of independent-minded solar array owners with deep pockets. And if the utility policies become too harsh against solar, those customers will open up their wallets to opt out of the system. And I think that's a failure in energy policy if we have customers willing to spend more money to go off grid than to put that money to use in other applications, like doing more renewable energy rather than less. Now, rapid shutdown is a design issue in the solar industry. Rapid shutdown requirements have been increasingly harsh. So in NEC 2014, when rapid shutdown first came into being, they said that there's a 6-foot perimeter around the solar array, and any conductors from the array going outside of this 6-foot perimeter, those conductors have to de-energize on command. They don't, and so in NEC 2017, they've actually kicked it up a notch, and they've said this 6-foot perimeter is now a 1-foot perimeter. And so even your jumper cables that go from one array section to the next, if they go outside a 1-foot array perimeter, this jumper cable has to be able to be de-energized on command. And so, either you're doing micro inverters and putting a little box behind every single module on the rooftop that when there's a power outage, it can kill the power right at the module itself, or you use a rapid shutdown combiner box. Even if you're actually not combining the circuits together, there are boxes on the market now that you put next to your array or under your array that you run all the circuits back into, and you kill the power at the box. So you can use these rapid shutdown combiner boxes as long as your solar array is continuous. If you have subsections of the array where you have a jumper cable between one array section to the next, you might still want to stick with module level panel electronics. Well, then we get to battery banks, and we say, well, now wait a minute. If my battery is designed to make me not lose power when there's a grid failure, how does that relate to rapid shutdown? Because won't the fire department show up to my house because my building's on fire, pull power to the property, and their concern is that you have these live wires from the solar array going outside the array perimeter. And so if my battery bank turns the solar array back on, now they think the power's out, but my backup system is clicked back in. Well, if you have a generator backup, generally the generator is located near your point of interconnection. And usually there's a disconnect switch on that generator. So, if you have a house with a backup generator and the fire department shows up, they pull the power to the property and they can quickly identify the generator and that generator disconnect switch and turn the generator off as well. But now you might have a battery bank inside the building and a disconnect switch for the solar array outside the building. And so what's the fire department to do? They flick the switch and they think, well, it's already de-energized. Rapid shutdown requirements in terms of the battery cables within 1 foot outside the battery bank have to de-energize. That stuff has not come into play yet. There are also disconnect switches that you can buy that will either use Wi-Fi communication or neutral wire communication or hardwired Ethernet communication, where you might have Ethernet wiring between your battery inverter and this particular kind of box that will serve as a system level emergency shutdown that'll shut down everything at once. And I'm not so sure that that's the best idea, because if you locate a system level shutdown outside the building, to me that can invite more opportunity for pranksters to turn your building off than the fire department to get much use out of it. But then again, you have to be able to give the fire department a way to turn off your backup system. So it's not really the best way to do that is not really well defined in code at this time. What is in code is to say that your backup systems and your emergency backup systems, the system level disconnect for your backup system has to be located in a different spot than your main service disconnect. And so like on a generator, the fire department shows up and they pull power to the building, but they see the generator. And there's no confusion on, if I pull the power to the building at the meter, does that kill the whole building? They see that there's a disconnect in a separate location for the backup system. And so what that means is, if you want to have a system level disconnect outside the building, it has to be physically separate from the other disconnect switch that you already have for your solar array. So that it will be a code violation if you put a disconnect for the battery system, for the backup system, right next to your solar array disconnect. That solar array disconnect is not part of code. It's a little confusing. So anyway, another thing to think about this slide is, just like with these rapid shutdown combiner boxes, the way these rapid shutdown combiner boxes work up on the rooftop is that this is a DC system, and so you have a positive side and you have a negative side. There's no neutral involved. Well, on these rapid shutdown combiner systems, you'll still run a neutral wire up to the rapid shutdown box that's just used as a relay to enable the rapid shutdown functionality. Now you might have some disconnect switches that have additional intelligence built into them. So I don't use the system level disconnect buttons to tie everything together, mainly because they're so infrequently used on the market that they're still pretty expensive. So I don't think that it's worth buying them now, but it is worth it to just keep a space for a system level disconnect. And when you're doing your battery systems, you want to indicate in your signage outside the building that there is an emergency backup system in place, with showing the fire department where to go in order to turn off that system level disconnect. And in solar, there's been this kind of push by the utilities to develop rules and regulations beyond what's required by code. So code would say, hey, as long as your control room is right inside the building, you can locate your disconnects right inside the building and direct the fire department to right inside your building where all these disconnect switches are. The utilities have pushed back on that, saying, no, we want these disconnects to be located outside of the building. And so they can go and turn off the solar array outside the building, but that doesn't impact your ability to use electricity from the grid. It's just a shut-off switch for the solar array. If you put a disconnect switch for your solar array plus the battery bank plus your power outside the building, that's a little bit more complicated. So you might, if you have a system level disconnect option, that will probably be placed inside the building or in a lockable box outside the building, in a separate location from your solar disconnect. At the same time, you know, right now utilities are asking you to buy an AC knife switch disconnect for the solar array itself, and that's not part of code. So when we think about automatic transfer switches and system level disconnect budgets, you know, maybe you can negotiate with your local jurisdiction to say, hey, we do, you know, what we plan to do is have a system level disconnect right inside the building for the whole system. Can we use that instead of a solar knife switch disconnect, and make the point that the solar array is already landing on an accessible disconnect right inside the building, and it would be confusing to the fire department to have a knife switch disconnect outside the building for the solar array that doesn't de-energize the emergency backup system. You know, I think that that could become kind of a mess down the road, you know, well, with good intentions, but let's see. Solar cable costs about 28 cents a foot. You know, well, the difference is the solar cable being rated for 2,000 volts has a little bit of a thicker jacket on it than regular THWN wiring. And there's this little -2 adder that reflects environmental resistance. And so your solar cable costs a little bit more than THWN. I recommend when you go into that conduit and you're inside the building for your home run back to the inverter, not staying in solar cable, but transitioning into THWN2. And the reason is not necessarily because the solar cable isn't good. The solar cable is more robust. It's not necessarily to save money because, you know, THWN2 might cost 18 cents a foot. The solar cable costs a dime a foot more, but we're only talking about maybe 100 feet of cable or up to 500 feet, you know, 10 to 50 bucks. That's not worth the complication of dealing with multiple kinds of wire on the job site. But just remember that this PV cable is designed to go outside of conduit, and it has a thicker jacket. So what happens when you put it inside of conduit? Well, you get less airflow in that conduit, so it's going to retain more heat. And then with your thicker jacket insulations as well, there's more mass inside of that conduit than airflow. So I just think it's better to use THWN inside of conduit because of heat. It's just a finer point. I mean, it's not a mandate. Your MC4 connectors cost anywhere between 50 cents to $2 each, depending if you buy them online. MC4 is the standard, but multiple manufacturers supply it. The big difference that I've found between manufacturer A to manufacturer B on MC4 connectors is that I don't have a picture of it. We'll probably be able to see it here. So just, you know, it's a standard connector, but there are nuances that are different. So here's an MC4 connector, and I don't exactly know which manufacturer this is. But what you can see here is this little metal piece. My laser pointer. I'm trying to pull up my laser pointer here, but I'm having trouble. What I want you to look at is at this metal piece where it has kind of this half cylinder at the top, and that little half cylinder gets crimped around a copper wire. And where the failure point can occur is that where the metal copper gets crimped around this little point, that can slip if the crimped connection is not very good. We can go look at some other MC4 connectors. You know, it's the same housing, it's the same plug. but instead of having the metal half cylinder, it has a full cylinder that it gets pushed into, and it crimps all the way around the wire and not just around 90% of it. In my experience, I found that these kinds of MC4 connectors are less likely to slip. So that's really on an install issue. That's not anything that a do-it-yourselfer would pick up on, but in the field, when you're buying your MC4 connectors, I like the ones that have the full housing around the actual copper, and not the ones that are this little half cylinder crimp connection that's a little bit weaker. You got to go into metal when you're in DC wiring. Not that I think inspectors today will be picking up on it, but technically, and that inside a battery room, because DC has to be inside metal conduit, it's common to see this metal flex conduit being used. Technically, inside your battery room, you should be using this plastic flex conduit with the metal inside. It just has a plastic layer around it. It's more expensive. It's more material. So liquid tight metallic flex conduit versus regular metal flex conduit. And the reason is a little bit different than what the solar installer might think of. What the solar installer knows is that DC wiring has to go into metal conduit. And the reason, if you're an electrician, you might think, well, metal conduit is listed as a ground path, and so maybe that's because if DC faults, then it has a path to ground. But really, that's what your equipment ground conductor is supposed to be taking care of. And that metal housing for DC wiring is simply to give it some additional protection, where ground faults with DC are more likely to cause fires than with AC. And so they want to give it a little bit more of a rigid protection to prevent, critters from gnawing on the cables. And so metallic flex conduit should be sufficient inside a battery room, except that it's subject to corrosion. And so where you have a battery that does off gas, it's best to use the liquid type metal flex conduit inside your control room. The goal is to achieve a pleasant looking solar array. All right, so let's look at some of the hardware accessories that go into a battery system. So what we're going to start out with is this service panel here. This is a service panel that says, look, we need a DC service panel because we have multiple charge controllers and 2 strings of batteries. And so the 2 strings of batteries need to be wired together. The charge controllers need to be wired together. They need to have a point of interconnection. And what that's going to be is a DC bus in a DC service panel rather than an AC bus in an AC service panel. And so, your inverter manufacturers will sell you a service panel to provide that DC combined connection. And then Schneider, and what's common on your battery inverters, they'll also put an AC side on that service panel. You're allowed to combine DC and AC side stuff together, but there might need to be a physical barrier that's integrated into the service panel itself. So let's see, we see 3 60 amp breakers plus 5 AC breaker expansion positions. 1 pair of 4-aught battery cables, factory installed and ready to connect. Then some number 6 wiring. Looking at the charge controller spec sheet, we see that it's designed for both 24 volt and 48 volt systems, but the 48 volt system is going to be twice as powerful, so might as well just do a 48 volt system anyway. PV operating voltage from up to 550 volts, no big deal. Battery voltage range from 16 volts to 67 volts. Just remember that a 48 volt battery, that's the nominal voltage. It can, usually a 48 volt battery can go all the way up to 60 volts. It just doesn't. It takes too much energy to charge it up to 60 volts. You would only be charging it up to maybe 50 or 51 or 52 volts during a battery maintenance cycle. We see the maximum charge current from the array, our wire sizes of number 6 to number 14. And so I'm generally going to be going in number 10 because that's the MC4 connector kind of cut off. And then we can see that this charge controller is set up to accommodate a variety of modes. Flooded, gel, AGM, those are all lead acid type batteries. Lithium ion batteries are commonly not at 48 volts. They're at a much higher voltage, maybe 300 or 400 volts. And so you can change the configurations of this particular charge controller to accommodate custom battery banks. Temperature ratings. This one was kind of an interesting one to me. We have ambient operation from -20 to 65. And then we have power rating above 45 C. And so I'm thinking, well, what is 45 degrees Celsius? I'm in the US, so I'm Fahrenheit. It's 90 or it's 113 degrees Fahrenheit. I actually think that if you go and you read the manual, they say 90 degrees Fahrenheit in the manual for power derating. So your battery inverters, generally you want to keep them in a dust-free, air-conditioned environment. They're not the hardy outdoor NEMA 3R inverters that you see in the solar industry. The warranties are also shorter. Your standard solar inverter has a 10-year warranty. The battery inverters have a 5-year warranty. Monitoring the system. The monitoring system becomes more important in an off-grid system because there's more parts. And let's say I had a SMA inverter, but then I had a third-party charge controller, like a midnight charge controller. Well, the problem is then when I want to monitor, the energy coming in and out of my charge controller and the energy coming in and out of my inverter, now I have two different monitoring systems. And that, what you want on a battery system is a comprehensive monitoring system so you can easily identify, if you're not getting the power to your battery bank, where's the issue? Is it coming from the solar array itself? Are my loads too big? Or is it an issue within my battery bank itself? It's a lot easier to diagnose that if you're all on the same platform. Let's see what this says. There we go. So what we would consider to be essential or standard accessories are often add-ons because you might be buying a battery system with its own monitor. You might not be putting a generator onto the system. So given that these inverters are so expensive, these kind of what we would say standard accessories are still, that you very well might need to get the full functionality out of your inverter system. You'll still be buying them separately. So for instance, this battery monitor on the left, that will monitor the temperature of the batteries and also the current coming out of the batteries. And that will enable advanced modes on the Schneider inverter to say that, okay, you might have what's called load shedding, where you have a critical load panel and a main load panel. And you might turn off the main load panel if the battery bank voltage drops down to a low voltage, you want to shed load. Well, if you're not monitoring your battery current and temperature and voltage, then you can't do that. On the other hand, on the high end of the spectrum, if your batteries are overcharged, you might want to turn on additional loads. I mean, at that point, the world is really your oyster. You could imagine a off-grid home with a water fountain in the middle of a plaza. And it might be that you turn the water fountain on when your battery bank is at the top of its voltage, and then you turn it off as the battery bank begins to decline. And so instead of having to monitor the system through your cell phone, you have this nice kind of organic water feature in the home that serves also as a subtle reminder to the tenants to reduce their energy use when the water fountain isn't working during the day. That would be when you dial it back a bit. So another accessory that's a little bit odd is in the Schneider product line, you have this digital display that allows you to program the inverters and get them set up. So you really need to have this digital display in order to get the system to work. And so you take the coming off the back of your Schneider inverter, and here's your Schneider inverter, and it has this kind of green display right here that doesn't have the LED screen on it. And you have to take that out and put the functional screen in that you actually need. It's a requirement to commission this system. And I'm just thinking, well, why don't they just put that screen on to begin with? Well, it's because you might be double or triple or quadruple stacking the inverters, and you only need that screen on one inverter and not four. So there are reasons that these kind of essential accessories are not included as standard features in the inverters, but you have to buy them anyway. And it's because they're what might be standard when you're only buying one inverter would become unnecessarily redundant when you're buying multiple inverters. The SMA battery inverter is a 120 volt output. And so you might need to buy a transformer to get it to 240 volt outputs. Or you could do a 120 volt output on each leg and get rid of the transformer. But then if one of the two inverters fails, you're out of luck. You don't have any backup for that. So you might need to buy additional transformers. And what SMA says is, well, look, if you're doing an off-grid system, you might just be running a 120 volt electric service, and you might not need this 240 volt service. Well, we're doing 240 volt split phase because we want the building electrician to be able, and the client to be able to install whatever kind of appliances that they'd be normally finding in Lowe's or Home Depot, and not just be restricted to 120 volts. And so you may be buying an additional transformer. Looking at some of these specifications, why don't we take a closer look at the Tesla Powerwall? It's one of the more popular systems on the, I don't know if it's on the market, but about to be on the market. So the Tesla Powerwall, the original one, it's 3.3 kilowatts, 6.4 kilowatt hours. So what that means is it's a 6.4 kilowatt hour battery bank, but it can only output 3 kilowatts of power. So it takes 2 hours to fully drain. One thing that kind of strikes me about the Tesla Powerwall is it's only rated for 10 amps. And 10 amps is not sufficient to run a household. So in order to run a household in the way that you or I would think of during a power outage, you would need multiple Tesla Powerwalls. You think about how many 20 amp breakers are on your electric service panel. You know, the Tesla Powerwall can only really power one of them, maybe. So it's a small battery. All right, now we're back on the Schneider inverter. This is a 6,800 watt inverter, but it has a 30-minute rating and also a 60-second rating that goes into a burst mode. And so it's a 6.8 kilowatt inverter, but for 30 minutes, it can actually go up to 8,500 watts and then up to 1,200 watts for 60 seconds. So given that we're double stacking these, our system, it normally is outputting about, it's under normal operating conditions, under a continuous load, it could output up to 13 kW, which is fine. You know, yesterday we saw the real-time data of a southern home of the peak demand getting up to 14 kW. Well, you know, if it were to get up to 14 kW for a half an hour, you know, this system could actually deliver 17 kW for a half an hour. And so this system is well sized to accommodate our air conditioning loads, and even it can burst up to 24 kW under 60 seconds. So it can handle some level of inductive heating and cooling and variable loads. That said, when you get up to 90 degrees Fahrenheit, it derates a little bit. So it is better if you want full power output from your inverter, a battery inverter. You're not going to get it if you locate the battery inverter outside. We're going to get our maximum continuous output ratings, frequency. I don't really have much to say about the rest of this stuff. You know, if we're dealing with its maximum output current under a 60-second rating being 52 amps at 240 volts. You know, most electric service panels are 200 amp panels. And so if I have a 50 amp output, you know, really two of these inverters would only get me up to 100 amps. And that's where a generator can come in and say, okay, well normally on a home, you're not pulling 200 amps. You're pulling much less than that. But on a solar array like this, we're only getting up to 100 amps. So what happens when my client wants to throw a New Year's Eve party and they're running the, you know, all the ovens and all the burners on their stoves and all the lights in their home and the air conditioning? Well, at that point, the generator can click on and provide the rest of the power that would be typical for a 200 amp electric service. So we see the charge controller being rated for a variety of charging phases. Its output range is 48 volt nominal, but we can see that it can output even higher than that. So it can charge the battery during its maintenance. It's called equalization. The battery temperature sensor is included. We'll be taking a closer look at that later. This was one that was interesting. Then you get a battery bank range, and it goes from 440 amp hours up to 10,000 amp hours. And so what that means is there is a minimum size to these battery banks, where if you put a small battery on a large output, it can push too much power into the battery. So there is a minimum size. I mean, you look at it, 440 amp hours times 48 volts is going to get you up to about 9 kilowatts or so, kilowatt hours per battery inverter. And then we have the AC input. We have an AC input 1 and we have an AC input 2. This is perhaps one of the more differentiating features of the Schneider battery inverter than, say, the Magnum battery inverter. As some of your battery inverters, they only have one input. So it's either you get a generator or you get the grid. You know, when you have that grid connection there, you don't really need a generator because you can get all the power that you need for your battery maintenance from the grid. I like having two AC inputs because for me that means flexibility. You know, we don't really know where the market is going to go down the road, but what I know is this client is going to have an aging lead acid battery bank, and eventually that lead acid battery bank is going to start dropping in capacity. And what I would like is to extend the life of that battery bank rather than replacing it once it becomes to the point where its capacity is dropped to the point where it needs to be replaced or expanded. What I'd like to do is go and add an additional battery bank as a grid input. And so by having this kind of reserve grid input there that we're not using, that gives us an expansion for the array down the road. You know, you call up the battery manufacturers and you talk to their tech support, and they say, well, we don't support that at this time, but that doesn't mean the inverters aren't capable of it. It's just that they're not, you know, the tech support is not going to provide you with the design assistance to set up a microgrid. They're gonna, you know, force that onus onto your electrical engineer. You know, so essentially you can combine battery banks of multiple chemistries, but you're on your own for that. And what you'd have to do is monitor your grid just like the power company currently does to make sure that your grid levels are not getting out of whack. 8 millisecond transfer. And then these battery inverters can also be used for frequency correction on the grid as well. And then finally, we get to like the environmental ratings. And so these battery inverters have the same form factors as your old school solar inverters. So they might not be NEMA 3R. The Schneider inverter is NEMA 1. So it really has to be inside. It can't be outside. You know, your battery inverters, this is a heavy inverter. It weighs about 120 pounds. You know, some of your batteryless solar inverters now are getting very lightweight. These are the ones where you might need two people to kind of wrestle up onto the wall. The warranties are less. We've talked about different modes of operation, whether it's generator support or peak load shaving, or prioritizing selling to the grid rather than charging the battery, or prioritizing charging the battery rather than selling to the grid. And then finally, there are these auxiliary relays where you can enable load shedding or load dumping depending on the state of charge of your battery bank. Okay, so we're halfway through today's program. So what we're going to do now is take about a 15-minute break. When we come back, we're going to look at some wire diagrams of these batteries, and I'll kind of point out where some points of confusion might be. So why don't we go ahead and take 15 minutes. It's about 12:38 now. We'll pick back up at about 12 till. So 48, 53. No, we'll pick back up at about 7 till. So let's take a break, 15-minute break, and we'll see you back here in 15 minutes. All right. Welcome back. We'll give everyone a couple of seconds to get back into it. We had a question over the break on what is the difference between a charge controller and a battery inverter. And I think it's a pretty good question, and it gets back to AC and DC coupling. Um, let's look at a couple of different battery inverter configurations. Here we have on the left, bring my things set up here. Just bear with me. Pointer options and laser pointer. Oh, come on. There we go. So this is the SMA battery inverter. And here is their service panel that is for paralleling the two batteries together. This is an Outback battery inverter, and then there's 4 charge controllers next to it, and here are their service panels for paralleling everything together. Then the Magnum inverter with the service panel for paralleling everything together. And so in these systems, you have battery inverters, and then you have charge controllers. And I want to bring up another example. This is more of a real world example of where, residential storage. This is the SolarEdge inverter. And, what we have here in the SolarEdge inverter is we have the inverter here on the left, and then upline, we have, I guess it's a little harder for me to pull open my tools when I'm using my browser view. But here we go. So upline, we have these little boxes that go behind every module on the rooftop. And these, you might think of them as microinverters, but in the SolarEdge system, they're called DC optimizers. And they regulate the voltage coming out of the back of the module. So, your solar module voltage fluctuates. It's designed for a maximum voltage of 600 volts, but it's going to be operating more along the lines of 350 or 400 volts. What the voltage regulators do is they say, okay, well, it's all designed for a maximum voltage of 600. So why don't we step the voltage up to 600 or 550 or whatever? And by increasing the voltage, you drop the amperage. And that means on a number 10 gauge wire, you can get a couple more modules on a given circuit. And there's also some shade mitigation advantages where, even if you have one module shaded and another module not, the voltage regulator will either adjust the module voltage so that your shaded and unshaded modules no longer impact each other, or it might just take the module completely out of the circuit. But regardless, from the inverter perspective, now the inverter is getting a constant voltage rather than a variable voltage. And that actually allows, even though the DC optimizers you're buying more components, so the total system cost is a little bit greater than if you didn't buy these boxes. The inverter itself is a little bit cheaper because it's being dealt a constant voltage. And batteries are the same way. Batteries, you want to send your batteries a constant voltage. Now, your battery inverters are also voltage regulators in the sense that any power coming into them and then going out to the battery, that's a regulated, constant, controlled voltage. So your battery inverters are voltage regulators. They go from AC to DC when backflowing through the battery inverter into the battery bank itself. Your charge controllers are kind of like the Solar Edge system here. Your charge controller is just like the Solar Edge optimizer, except it'll handle the whole circuit of modules and not just one module. What it'll do is it'll take that varying voltage coming out of the array and fix it before it goes into the battery bank. So yesterday, we were talking about DC versus AC coupling. And so we had a choice to say, okay, well, we can either do DC coupling, where we're going from our array through a charge controller into the battery bank, and then from the battery bank through the battery inverter into the load, or you could do AC coupling, where you dispense with the charge controller. And so under an AC coupling, and I apologize for this being a little blurry, but under an AC coupled situation, there is no charge controller. You don't have the solar array going directly into the battery bank with a charge controller in the middle regulating the voltage. Instead, under AC coupling, your solar array is being managed through a inverter, and so you have a constant voltage output. In that case, that would be a 240 volt AC output. And then you go from your battery inverter, and then you get your constant voltage being regulated by this battery inverter into the battery bank. So the real difference between using a charge controller versus an AC coupled system is that it's a choice between buying a whole extra inverter versus buying a charge controller. And the charge controllers cost about 2/3 the price of the solar inverters themselves. So that's why in off-grid new construction, it's very common to see a DC coupled system having the least amount of capital cost up front. We also saw the a startup Pica that, basically what's happening here is that they're putting an upline charge controller or string optimizer or whatever you call it, just to regulate that voltage so that that home run between the solar array and the battery and the inverter is at a constant voltage. So in a sense, your battery, if you're flowing your energy through the battery inverter into the battery or straight from the array into the battery, the charge controller or the battery inverter accomplish the same thing. In an AC coupled system, you just get rid of the charge controller and you have DC to AC inverters accomplishing all the tasks. Whereas in a DC coupled system, you save a little bit of money up front by going into a DC charge controller system. So going back to our Solar Edge example, here is the LG Chem lithium-ion battery, and it's compatible with the Solar Edge inverter. And the reason why it can be just kind of seamlessly integrated into the Solar Edge inverter system is because the customer has already effectively bought a charge controller by buying these DC optimizers that are a little bit upline. And so now, because this voltage is being regulated at a constant voltage into the inverter, it's not too hard just to snap on an additional battery. In fact, what becomes more complicated about it is what is the voltage of that? Most battery inverters are at a 48 volt system, whereas the Solar Edge system is outputting at 500 at a higher voltage. And then we go back to the way that LG Chem addresses this issue is they have two different options. They have a 48 volt. Here we go. They have a 48 volt option for going into a traditional 48 volt battery inverter, but then they also have a higher voltage option that's going into, say, the Solar Edge inverter. And generally, it's better to be at a higher voltage than a lower voltage in these kinds of applications. It's slightly more efficient to be at that higher voltage than the lower voltage. And so when we were doing our upfront design evaluation, we had to make a choice between DC coupling and AC coupling, and that's a choice between having a charge controller and a battery inverter versus having a battery inverter and a separate solar inverter, and having the battery inverter and solar inverter being landed on the same AC panel. When you do a charge controller, you have a DC panel. A little bit more complicated, a little bit less upfront cost. Again, you're really only dealing with DC charge controllers when you get into residential off-grid. Otherwise, you're staying AC coupled, where you have the solar array on its own inverter and the battery bank on its own inverter, at which point there's no DC to DC connection into the battery, at which point you don't need a charge controller. All right. And so here we have on the picture on the right with our Outback inverters, we have the charge controllers being wired in parallel, and that's probably occurring at this point right here where we got 4 breakers. We probably have the charge controllers coming up onto a common DC bus that then the battery inverters get wired into. I'm not sure what's going on inside of here. Haven't done a Outback system. With the SMA system, you would either have a midnight charge controller that gets attached to kind of the top of the inverter, or you would just have a standalone SMA inverter on the side of it. So looking at some wiring diagrams, we have our grid, our solar inverters coming in from our battery bank. We got 2 inverters being wired in parallel to each other, and then coming into our load panel. And it might be that there's a transfer switch already built in to these inverters so there's no external transfer switch, where we're using the transfer switch inside the inverter itself to protect the entire home load. And so where these inverters would want to be landed in order to do this is you have your utility meter coming in from your grid connection, and then you have your home load panel. And usually you're tying in, for residential, you're tying in the solar array onto the bottom of the bus bar on your breaker panel. But where this would be tied in order to take advantage of the transfer switch built into the system, is halfway in between. So that's a supply side connection or a line side tap. You get your knockouts on the bottom of the inverter. I actually learned something new for me in code, is that it's much better to use the full knockout when you have these concentric knockouts, because when you use just the middle section and not the exterior section, that's no longer a ground path. So if you're going into the middle of a concentric knockout rather than the external, you have to use a grounded bushing and connect your metal bushing to the ground of the metal case. So you get layouts for your Ethernet communication ports. You can see where the battery inputs are sized for much larger cable than the solar array itself. Here we see inside this DC and AC service panel here's a bus that the battery bank itself is landing on. And we have a positive and a negative side with a breaker the battery is landing on, and then it's going into the positive and negative DC input of the inverter, and then that will separately come and have an output that lands on the AC side of the panel here. So we got an AC bus, and we also have a DC bus. And generally in a parallel configuration, so this is just for one inverter. Now we have two inverters, and we see from the battery bank side, now we have the battery coming in, and our two inverters landing on the DC bus, and our two inverters landing on the negative DC side. So I'm going to show you an issue that we actually ran into in the field this week, commissioning or getting our off-grid array ready for commissioning. Is there's an additional component called a shunt. And what the shunt does is it measures the current flowing out of the battery bank system. And that will enable you to, that'll enable you to turn off the battery if it's overheating. It'll enable you to enable load dumping or load shedding. It'll allow you to enable demand management. And so we were on our design, we were using 2 strings of batteries. And then we're landing our 2 strings of batteries onto this DC side here. Actually, the shunt is called for going in on the negative side. And so now we have our negative bus with 2 strings of batteries landing on it. And the question is, well, where do we locate the shunt? Because the shunt in this line diagram, it shows that you read the manual, and the manual is designed around 1 battery string. And so here we have our 1 string coming out of our inverters, and it's, in this picture from Schneider, it's already showing 2 strings of batteries, but we would land our 2 strings onto this bus, and at that point, there's no location to land the shunt. And so we got, my field electrician was telling me, well, I don't know where to land the shunt. And I'm telling him, well, look, it's in the manual. We have 2 strings of batteries and 1 shunt. We don't need 2 shunts. It should be able to be landed on it. But he says, well, look, we're not paralleling our strings at the battery itself. We're taking our 2 circuits of batteries and then running them directly back to this bus. So there's actually no location, where our parallel wiring is occurring right here, and there's no location for us to put the shunt in line before we run back to our inverters. And so actually it was both of us being dumb. The point was, well, we could still have our just ignore this stuff right here. And so we have our 2 battery circuits running back to our inverter, circuit 1 and circuit 2, and we ended up just double lugging them onto the shunt, and then double lugging them off of the shunt, and then running to that bus right here. So it really wasn't an issue. There was just no field instruction or field instruction manual from the inverter manufacturer to offer that guidance. So that was where our we had to sit down and say, well, if we paralleled them, well, we already have the cable here, and if we just did it to 1, then we're only measuring half the current. And if we have it in line with 1 circuit, not the other, that changes up the resistance, and so we don't want that either. And then we said, well, let's just double lug it. Of course, that's what we're supposed to be doing. If we had done 3 circuits of battery instead of 2, we wouldn't have been able to triple lug it, because that would have been a separate code violation, where if you have 3 circuits or more in parallel, you gotta fuse them. With 2 circuits, we don't have to fuse them. So we can just double lug coming out of the battery bank onto this shunt before we go into the inverter. Another inverter component that caused a little bit of confusion. This is the battery temperature monitor, and you're across at multiple points across our battery bank. This E, G, H, F, A, B. So we're monitoring the shunt as well, and C. We're taking voltage readings across the shunt and voltage readings at different points in our battery system to monitor the battery. So we have our battery monitoring system. You normally wouldn't have that in batteryless solar. So there's a couple of extra bits and pieces to install. Here's a line diagram where we have a generator, a grid-connected load panel, a critical load panel, and our solar array. And so this is where, with our off-grid design, we didn't have a grid connection. And actually, we're not trying to do a non-critical load panel. We're just trying to power the whole house. So we're dispensing with this panel, and just, everything is effectively a critical load panel at that point. And the complication we ran into was saying, okay, well, we know in normal electric code, there's a connection from the utility that establishes a reference between your neutral wire and ground. And it's only supposed to be made at one point. And so in your meter, your electric meter, right where the power is coming into the property, you have a ground connection, and you actually have, not on your side of the panel, but on the utility side of the panel, they're connecting the ground, the neutral to ground, and establishing a zero voltage reference across the neutral, such that when that neutral starts to have more voltage in it than it's supposed to, it'll open up your breakers. So what we got into on our point is, when we eliminate this grid connection, the question is, well, we've also eliminated where the neutral is being bonded to ground. So then here we have our neutral bar here, and so that's where our the field question is do we bond neutral to ground at that point? So there's only one neutral to ground in this kind of system. And so we have our generator on the same neutral, our critical load panel on the same neutral. And generally speaking, you want everything to be sharing the same neutral, particularly when you're grid connected, so that you can measure when the grid is available, when the grid is not available, and switch between your generator versus grid versus the battery mode. So not all of the wiring diagrams, you get a lot of different wiring diagrams from the manufacturer to accommodate a wide variety of design scenarios, but not everything is going to be straightforward. You got to rely on your electrical knowledge to say, hey, can I actually double lug onto a shunt? Hey, the plans don't specify where I'm connecting neutral to ground, but I know there has to be one neutral to ground connection. So where does that occur? You have to rely on your just general field knowledge or electrical knowledge for that. Now we got another wireline diagram. Here we have two separate solar arrays on two separate charge controllers coming in to one battery bank with two inverters and a generator and a grid connection and a critical load panel. And so we see what this is showing is the generator coming in to the top, the grid coming in from the top, the inverter outputs coming in from the top. This goes out to your load panel, and then there's bypass switches up here to help you, so that you can turn the inverters off and keep running off the generator if you had to place anything into a service mode. And so your inverter manufacturers will provide resources available to help you out with this. And I found that, at least right now, When I called up Schneider technical support, I don't get long wait lines. So, that might change in the future. For the past few months, they've actually been selling out of their equipment. So, let's see, battery DC negatively grounded, data center, communication center, whatever, battery positive DC grounded. What are your thoughts? I believe that you can ground the positive or the negative on a DC system, but generally the inverters are either floating or negatively grounded. So if it is a positively grounded battery, I think it will still work. I think you're and of course, on this spec sheet, it doesn't tell you which side is grounded at all. But so the question is, data centers and communication centers have a positively grounded battery. And David, I believe that these will work in a positively grounded setting as well. The one thing that I would kind of think about is, if you have a positively grounded battery, you may need to have the negative breakers as well as positive breakers. And that's kind of the extent of my knowledge on that. All right, so here's a project we did for Half Moon Residential. The owners of Half Moon, they had about $15,000 for a residential array, and their goal was to take their home off-grid. Well, we've seen that a residential off-grid system for a normal size, husband, wife, and 2 kids in the South would cost you about $80,000, and it's probably going to be around the same for the North. And we see we see the design scenario for winter and summer, with higher loads in the summer and less production in the winter, being about the same. And so we quickly realized that, hey, there's no way we can get a home to be off grid for 15 grand. So what the design was, well, let's get the most bang for our buck doing a $15,000 ground mount system, but let's just prepare it for going off grid in the future. So what do we do under that scenario? Well, the first is we're going to select an SMA inverter. And the reason why we went with the SMA inverter is because SMA also has a battery inverter in their product line. And so that we can seamlessly integrate a battery down the road. Now, this is not just typical for SMA. We see SolarEdge doing the same thing. But, that's really neither here nor. So, regardless, when you're designing a batteryless solar array, you may want to just go check out the product lines to see if the inverter manufacturer has a roadmap for getting into batteries. Most do, though. So anyway, here's our batteryless inverter system. We had 3 circuits coming from our solar array. We actually went and looked at the home electric bill, and they really needed not a 7 kilowatt solar array to meet their energy needs in an off-grid scenario. They really needed something larger than that. So when we did the ground mount array, we went ahead and ran the underground lines for an expanded solar array, so that this is only part of the total plan. Down the road, when they go off grid, we're going to about double up on our array size, but the wires are already in place. So that means we won't have to re-rent the trencher when we expand the solar array down the road. Now, if we really wanted to fine tune it, I suppose we could have gone ahead and poured the foundations and laid the piers for that, but who knows when that expansion will be. The problem with solar ready design, when you're trying to plan for expansion, you have to kind of find the right line between doing too much and doing too little. So one thing that we thought about doing was getting rid of the knife switch disconnect. So here we have our knife switch disconnect. That's a utility required mandate, but it's not part of National Electric Code. So what we told the utility originally is that we weren't, we were doing, here's our supply side connection. So we got underground lines coming up from the utility. Ignore this. This is a separate service for a heat pump. That's a standalone utility program. But we got our underground lines coming up from the utility, going through our meter. And then at this point, this is the pass-through box that's going into the wall. And on the other side of this wall here, you'll find a basement with an electric service panel. So all this guy is right here is a junction box for our supply side connection. Down the road, we're gonna have to add a battery inverter, and maybe that'll go outside if the environmental conditions are right. But the battery bank is more than likely going to go inside, and so this is right by the garage. It's a little off picture, but their garage is large enough to house a battery bank, and so we've kind of given us the space to expand the system with a battery inverter and a battery bank. And then down the road, this knife switch disconnect might go away, and instead of, we might keep this box, but we might actually land a separate, in addition to landing a battery inverter, we need to have the space to land our electric service panel. So most installers, when they're speccing out a job, they're only looking for about 3 feet to land the solar inverter. You might want to make it more like 9 feet of space to be able to land an inverter, a battery inverter, and a service panel. How much will it cost if we wanted to take this setup and add batteries to it? And so this is, you're designing a solar array for a customer and you want to pitch them batteries as an add-on. And so we're doing an 8 kilowatt solar array, but then we have to go and buy a DC distribution panel for the charge controllers plus accessories. The charge controllers themselves are a little bit less expensive than a standalone inverter. If we went with a standalone inverter and bought the battery inverter, we could wire them in parallel to each other, but we're still going to be buying a service panel to wire them all in parallel before we get to the supply side tap. So you're buying a service panel, you're buying all the additional battery temperature sensors and generator auto starts and automatic transfer switch to isolate yourself from the grid. And so those accessory costs add up too. And then you get to the price difference between a separate inverter or a charge controller, and it's in roughly the same price range. Or you buy a separate standalone. So I guess what these bullet points are saying is that either I could take my current batteryless inverter and upgrade it to a battery inverter plus a charge controller, or I would have to buy a standalone battery inverter that's large and that is separate from my existing system. And so that's going to cost me about $1 a watt, or to not have a AC coupled solution, but do a DC coupled solution. It's still going to be pretty expensive even before I get into the batteries themselves. And so to take this batteryless setup and add batteries to it, we're going to have about $6,500 in additional inverter parts. And then if we wanted to do the smallest battery possible, and go with a zero maintenance battery, the smallest battery for the SMA battery inverter with a maintenance-free lead acid battery is, it's going to cost about $9,500 in order to take today's batteryless solar projects and retrofit them with batteries. Now that's where perhaps selecting, say, SolarEdge gives you a competitive advantage, because with the SolarEdge system, you've already bought the charge controllers. And so it's going to cost you a little bit less to upgrade with batteries on SolarEdge than it is with string inverters. That's why I'm kind of waiting on with bated breath for string level optimizers, kind of like what Pika is doing, because that'll take the increased cost of the SolarEdge system and drop it down a little bit. So is it worthwhile to go off grid? Well, Half Moon's meter fees in Eau Claire, Wisconsin are $30 a month. And let's say so anyway, so for it's really, for residential, it's a question of, is spending between $7,000 to $10,000 for a battery that is going to be between 7 kilowatts to 27 kilowatt hours to 20 kilowatt hours, and that's not enough to run a home like you and I would think of. Is that enough to get customers in? And it really just kind of depends on how frequently that customer is actually losing power. And so we see residential customers buying these batteries not for economic reasons, but because they have the money to spend and they want that security, and they'd rather have all the energy they want during the day and a little bit at night instead of buying a generator. A generator would still be a cheaper way to go. Now, is it worthwhile to say, well, what if we're doing our own battery maintenance and we're using the cheapest batteries on the market, which are like flooded lead acid golf cart batteries? And so let's go off grid to save on this $30 a month meter fee. Buying a giant battery bank just to save on these meter fees at $30 a month, you're not going to get a payback on that. So we're going to have to see meter fees go up to something like $60 to $100 a month before solar customers use that as a motivation to go off grid. Energy Toolbase is a software we looked at yesterday that is very good at the economic modeling of commercial battery banks. And so now we say, okay, well, residential is a non-economic market, but it's so cheap, or relatively cheap. I wouldn't think 10 grand is cheap, but you'll find the customers who are buying batteries in the residential market will spend that money just to have a little bit of security and not expect an economic payback. Commercial demand management is about economics. And so Energy Toolbase is a software that's based around economic modeling. And essentially, to model demand management, you have to look at a 30-day range of your building demand, and then kind of guess or set the level that you want to demand manage. And if you want to demand manage more rather than less, the further into this curve, if we, instead of load leveling at this point across the board, if we wanted to load level down here, we would have to be running our battery for a substantially longer period of time. So there is kind of an optimal point on, cost and battery runtime to say, when you're load leveling these short, spiky peaks, that's going to be a lot more cost effective than trying to demand manage all the way down to your building's base demand. And so, for that extent, a smaller battery bank on a commercial facility is going to do more for demand management than a larger battery bank in terms of cost savings per watt, although you do get economies of scale for a larger array. And so what Energy Toolbase will do is it'll take your 1 year's worth of data of facility usage. It'll take your actual rate structure for inflow versus outflow, for demand versus energy, and it'll take your project installation budgets and run it through a financial optimization calculation to tell you what your optimal array size and optimal battery bank is. And it's not that you can't do that using pencil and paper, but you're doing a very complicated calculation that's going to vary by the time of day, the month of the year, extracting 365 days of data input. It just gets to the point where the accuracy of software is greater than what you can put together on your own. And then also, this serves as a good illustrative example, is the best customers for demand management are the ones that have really tall, spiky demands rather than a sustained load throughout the entire day. Although if you do have a sustained load throughout the entire day, that's where solar comes in and it reduces your load in the middle of the day, and then the batteries can come in and take out the peaks. So there are good synergies. Looking at this California incentive, what we have is a $180,000 battery bank, and in California they get a battery incentive on top of that. And so, effectively what they have is a $140,000 battery bank, and they have no solar in this example. And I don't know if the costs in this example are that accurate of today's market conditions, but what I really want to show you is the effect of the payback when we go from the batteries by itself to the same case study with solar, what happens to the payback. We have a 122 kilowatt battery system with an 86 kilowatt hour battery bank. And so that would be reflective of a very spiky demand management curve where they're actually, the battery is designed to fully drain within, less than an hour's time. Whereas, like, say, the Tesla Powerwall is designed to fully drain in a 2-hour time. So this is kind of a custom-built solution. We got our energy use and our electric bill cost. And what we see is we have our energy cost and our demand savings. And so, and the text is kind of small, but we have before our energy cost was $22,100. And then after our energy cost was $22,350. And so it does cost us some money to charge the batteries. And so the money that it took to charge the batteries was about $150. And then the demand savings go from $56,000 in cost to $38,000 in cost. So we save 40 to 56. We save about $16,000 in demand savings. And so you really don't have to worry about the efficiency of a system with commercial, because even if the system were half the efficiency, if it costs us $300 to charge the batteries rather than $150, that really doesn't matter because we're saving $16,000. And so whether or not I use the most efficient battery inverter, whether I use the most efficient battery inverter or the less efficient lead acid battery or nickel iron battery is not really the point. It's just that the demand savings are so great. And for that matter, in off-grid, you're oversizing your solar capacity to the point where for most of the time in the spring and the fall and most summer days and sunny winter days, your efficiency doesn't matter either because you're overproducing. You've designed your array to be much larger than normal. And so what that means is it's kind of ironic in off-grid and in commercial demand management, the efficiency of the system is not really a critical factor. So anyway, just with the battery bank, we're getting under this California case study a 10-year payback. They run some optimization. They run some optimization and they say, okay, a 29 kilowatt array or a 57 kilowatt array, you're still doing these spiky curves, and it really doesn't matter. You get kind of linear savings. But then when we get up to an 86 kilowatt hour battery bank, we're getting further down that cone. And by the time we get to 114 kilowatt battery bank, now we're getting more into base load demand management. So really our most cost-effective battery bank size is 86 kilowatts, and that's going to be custom to your facility based on how spiky your application is. And then the energy costs are not that sensitive. And so then we go and we add, and then what's also nice about the Energy Toolbase is they have the batteries spec sheets programmed into it, which is nice. There's another software called the System Advisor model. That's the big brother to PV Watts that you can do a little bit of modeling into it. But the difference is with the System Advisor model, you have to program in your own spec sheets, and the data on the spec sheets is not as reflective of the battery real life performance conditions. And then also the, with System Advisor model, it's just kind of, you're putting in assumptions about your building demand profile and kind of assuming that demand is going to be true for every day of the month, whereas you're using your actual data in more commercial software. So now we're adding a 200 kilowatt solar array to this commercial example. I guess I didn't put the concluding slide on it. But effectively, what we see is that the solar array will also have around an 11-year payback. But by adding solar, if the battery bank by itself gets a 10 to 11-year payback and the solar array gets an 11-year payback, effectively what you're doing is you're qualifying the battery bank for an additional 30% federal tax credit, which might not be the most noble reason to do solar on a battery-based system, but effectively that adding solar to the battery will do two things. One, it'll qualify the battery bank for the federal tax credit. That'll drop this 10-year payback down to about 7 years. Two, it'll allow you to get further into this load leveling curve, whereas with batteries on their own, you might only be able to get so far into it. But then by adding solar to take over your building demand management in the middle of the day, you might be able to get a little bit further into your demand management before you get into diminishing returns. Now here is a cost projection of lithium-ion battery costs and where they should, where the industry thinks they will be. So let's pull up our example of our LG Chem battery. I've from the distributor, this 10 kilowatt LG Chem battery. It's a 10 kilowatt battery, and just the battery itself. So this is when you add it to the Solar Edge system that already has the charge controller and battery inverter set up. so this is just the battery cost itself. You have a 10,000 watt hour battery bank, and it costs $6,000, and so effectively it's going to cost 10 kilowatts divided by $600 is it's going to cost no, it's the other way around. $6,000 divided by 10 kilowatts is you're effectively at about $600 a kilowatt retail. And so looking at this chart, here we are in 2017, $600 as the retail price for the LG Chem battery. So we're kind of on the high end of this curve. Now this is a cost curve of production. And so what that implies is that, the bare minimum, it implies that LG Chem is already at below a $600 a kilowatt hour cost for their batteries. And if they're operating at a decent margin, they might be at $400 or less. Now, Tesla claims that their hard costs of their lithium ion batteries are around $140. Now, that's great, but I can't go out and buy a Tesla battery. But what that's saying is, the industry lithium ion battery costs are well on this trend. If anything, the costs are below where the reports are. And that's pretty much true of any exponentially growing industry. The reports that are all projections on the industry are usually more conservative than the actual industry growth. And so what we're seeing is maybe in, by 2020, we'll see our cost of the lithium ion batteries be around $250 a kilowatt hour. And maybe the price of the LG Chem battery at that point will be 30 to 40% less than it is today. So there's really no reason the only reason today to go out and do your battery project today is that you still get the federal tax credit for it. And it's a big if, but if Congress overhauls our tax code, it's clear that the solar tax credit will go away. So you really, right now there's a good opportunity to do small battery banks at the commercial level for demand management, to collect that building data and qualify for the tax credit. Now we're doing, this part of the program is for some kind of updates to solar systems. Let's see here. I'm getting kind of to the end of my content, battery content at least. I'm trying to think about some other things to say before we kind of conclude and go into more solar topics. Let's see, here is our battery bank. So these are our industrial forklift batteries. And one thing that I really actually came to enjoy about this particular battery bank is that the batteries already came enclosed in a protective case. And so it's really, we just have to make sure that it's on a insulated mat. You can get a little bit of voltage going across this battery case leaking out of the batteries. So you can get a little shock if you go in and touch metal. And paint is not the best insulator for that. And so if you're putting your batteries on a metal rack, you need to make sure that the rack is grounded, and also that between the battery and the rack that you're putting some insulating material there. Looking at a different battery bank, here's where they're using smaller batteries that are, you could hand lift rather than machine lift. These are LG. These are iron Edison nickel iron batteries. Anything else to? So doing some updates to solar arrays. National Renewable Energy Labs, this is where they say solar costs should be today for string inverters. And it's actually kind of funny because the quotes that I see are more in the $3 a watt range. And so NREL is saying that, hey, project prices should be lower than that, but they're not. The market conditions are keeping the cost of solar high. Some of that I think has to do with the tax credit. If you're getting 30% off, there's more of an incentive to front load your project costs, go with higher end stuff. But they're saying balance of system material for your solar projects is around 19 cents a watt. My experience is that it's lower than that, but I put a lot of thought into optimizing balance of system material cost. Module prices, right, we bought our modules for the off-grid project at 50 cents a watt, but that was from a manufacturer made in America, Suniva, but they were on the verge of bankruptcy. They actually went bankrupt. They're trying to fight to stay out of bankruptcy, and they're the ones responsible for the import tariff anyway. So we went, on our off-grid, we said budget is an issue. We're going to buy more modules than we need to at a discount rate, and that's going to be our insurance against the modules not working down the road, is that we have a few extra modules and we got them at a really good price. But 64 to 65 cents a watt is typical for a good module efficiency of a 60 cell module. However, if the import tariff goes through at the level that was proposed by Suniva and Solar World, the minimum price of a solar module imported into the United States, and even Solar City that has a production facility in Buffalo to make solar panels, even them, they import solar modules into the United States. There's a solar manufacturer called Canadian Solar that makes solar panels in China. The vast majority of solar panels are made, are going to be subject to this import tariff. And that's going to raise module prices to at least 78 cents a watt, because that's the floor plot price. So we might see module prices go up by about 20 cents a watt in the near future. Inverters, NREL says their inverters are at 15 cents a watt. My inverter pricing with going with higher end inverters like SolarEdge or SMA comes out to be more like 30 cents a watt. But what we're seeing is, by buying some more advanced feature, by buying a more expensive inverter, you get better advanced features. So for instance, what we really like about this SMA inverter, I don't like SolarEdge. I don't like Enphase. They're very popular. When you combine SolarEdge and Enphase, it's the majority of the market share in the United States. So I'm definitely running against the grain when I say that. But what I don't like about SolarEdge is because you're putting a box behind every module on the rooftop, that box becomes a failure point. And my philosophy is to get rid of as many failure points on the roof as you can. And so we went with, even though the SolarEdge system is a little bit more battery capable than SMA out of the box, to prepare this site, we were fine just going with SMA and then adding a battery inverter down the line. But what SMA does get us is two things right off the bat. One, the SMA inverter is able to curtail the power output, so that when we do add a battery inverter down the road, we're going to be able to use more of the solar array and less of the battery bank, because we'll be able to take advantage of that feature. And in the meantime, what SMA has is right here is this is a power outlet this gets stuck to the side of the inverter, and you can actually, it's a separately derived power outlet where you can get up to 2 kilowatts of power out of it when the grid is down. And so even without batteries, the SMA inverter is able to produce some power through that controlled outlet. And this doesn't have to be an outlet on the side of the inverter. If I had to do this project all over again, you know, what we might have tried to convince the client to do is provide us some additional budget so we could take that outlet and actually move it inside the house so that during a power outage, they have a little outlet that they can use to plug into and charge their cell phone, or even charge up a portable battery during the day so they have some electricity at night. You know, maybe not enough to run anything more than their refrigerator, but you know, that gives them some options to have some form of backup power without spending the 10 grand to upgrade the batteries at this time. The solar racking, NREL to me is coming in low. You know, when I do my racking budgets, a lot of solar racking is designed for 6-foot or 8-foot on center penetrations. Whenever I do my structural reviews, I don't see a reason not to go with a 4-foot on center attachment staggered. But by the time you do 4-foot on center attachments and you're flashing them all, you know, that racking budget goes up. Labor budget from NREL, I don't really have any qualms or issues with. When I subcontract out the install to an electrical contractor, which the only way you can sub it out to an electrical contractor is having clear construction documents, and also having one person on the project who already has some solar experience. Maybe not the whole company, but I'll find that subcontract price for a licensed certified contractor to be in the 35 to 50 cents a watt. If I go to a solar company and ask for a labor-only contract, it's going to be much more than that, like $1 a watt for labor. Well, I can go to a just mainstream commercial electric contractor and get them to pull the permit and provide all the labor and equipment for substantially less than that. And what I've found is that your state licensed electricians are better at pulling conduit, bending conduit, and pulling cable, and no more of the beyond Section 690 parts of National Electric Code than your solar installers. So I really like working with general contractors on projects, but it requires more upfront project planning. NREL doesn't model any engineering costs to go into their residential project budgets. Generally speaking, the structural reviews are not required, and the 2-foot on center pine rafter with surface board rooftop is considered to be structurally sound for a solar array. But that, I don't think that's sufficient excuse, because I found that, you know, like with metal rooftops, for example, often the structural engineer will come back and say you need to do at least 2-foot on center or attached to every seam on the standing seam. So I think having a little bit of budget for your structural review will actually make you look more professional. You know, in terms of the solar array weakening the roof, I recently rehung or hung a new door in my door frame, and so I took the screws. You know, I have my wood door frame that I'm screwing the door onto, and you know, it's not that when I screw into the door the frame for the door, it's not like I'm weakening the wood by putting a metal screw into it. It's when I remove the screw and it leaves behind a screw-sized hole, that when I put the new screw back in, that connection is obviously weaker. And when I fill a rafter up with holes and leave them vacant and open, that rafter is weaker. So where the structural deficiencies in a solar array come from are not necessarily the upfront install, but when it does come time to replace the rooftop, you'll want to make sure that if you're taking the lag screws out of the rooftop as part of the rooftop replacement, that you're filling in the holes that they leave behind with a high strength wood glue to get that strength in the rafter back up. Profit, overhead, permitting, and supply chain. Generally when I'm doing projects, there's not like a commission sales rep and doing some competitive bidding. So that might be a price difference between these two. And so what we're seeing with NREL is in my budgets is we're seeing solar today should be around 250 to 270 a watt. When you get it installed through a turnkey specialty contractor, that price goes up to about $3 a watt. And even if this is the actual project budget for Half Moon's ground mount array, which we did in April of 2016. So a year and a half ago, we did a ground mount project for $227 a watt, installed by union electricians at $75 an hour. And that was done at $227 a watt. So I think the solar industry, there's still a big opportunity to get in and compete with the specialty solar installers, particularly if you have other things for your crew to do. Like if you're already building the building and you have roofers and electricians on site, absolutely you can get into the industry and be competitive. Let's see. Just doing a time check here. What's happening to my? Got about 15 minutes left. All right. So the next phase is, we know net metering's on the decline. We know that residential battery cost still has to fall by about half in order for batteries to start making economic sense at the residential level. So for the time being, the batteries are just kind of hanging out, providing backup power. We've seen how with demand management, the batteries actually have an economic purpose. And so what are some other options to increase the value of our solar project that are some low-hanging fruit? Can I get away with, can I do solar in areas where I don't have a good net metering policy? Do I have to have a battery bank that is so large to run my home without solar power for a long period of time? Just think about it. The solar industry for the past 10 years has been heavily subsidized, and the designs have been simplified because net metering means that we don't have to worry about inflow versus outflow. But like one thing we're doing on this off-grid home is we're using a deep freeze on a timer. And so the client has a deep freeze and it only runs between 10 a.m. and 3 p.m. And so it's not really ever drawing off of the battery bank. It's just drawing off the solar power, on days where it's not cloudy. Now you could take that a step further and get a programmable power outlet. But where the industry is right now is, I went to go look for like, hey, can we have power outlets that turn on and off as a function of solar production, so that we only charge the deep freeze when the solar production is high, and then when the solar production is low, it's just coasting off of its thermal mass. Well, there's no software on the market today that'll integrate your power outlets with your solar production. So when you go on like GitHub, which GitHub is a hacker community open source hacker community, you can find projects to integrate these wireless power outlets signaling with your solar array, but it's all in the early adopter, even pre-early adopter phase. But you can find, so what I'm saying is there is some low-hanging fruit out there, but you have to kind of, but there's not really professional solutions for load shifting. But being able to run your AC, to crank your AC, maybe using thermal mass to cool down your house during the day and coast at night, that kind of building selection, to say maybe you have an interior wall of your building made out of concrete so that you can blast your AC during the day and chill down that wall and buy yourself, not as much air conditioning use at night. Or what this company in California called Ice Energy does is they're looking at, maybe we can freeze blocks of ice inside of our air conditioning units, and that'll give us an additional period of time. Although Ice Energy, they're a small kind of startup company. Schneider makes a thermostat that will detect when people are in the home versus leaving, but it'll also connect to your phone's GPS so that if you've left for work and then the system detects that you're coming home, it'll turn the air conditioning on. That's, so there's a lot of like smart energy management devices, and it might be the onus of the solar installer to say, well, now that arrays are getting more expensive, maybe now that we're getting into right-sized arrays that are a function of the building load, maybe we take on more scope in terms of managing our on-site energy and seeing what loads the client has that we could push into times of solar production and take out of times of non-production. Or it might be things like taking your air conditioning unit and saying, okay, we're going to go with a variable frequency drive air conditioning unit that's always on, rather than one that has kind of a duty cycle that's on, off, so that we're not surging our battery load. That shouldn't happen. Sorry about that. All right, next slide. So another kind of low-hanging fruit out there is your tankless water heater, where over in Europe, what they'll do is they'll put a immersion water heating element into the tankless water heater, and that they will, whenever the solar array is detecting an outflow onto the grid, they use that to heat water. It might be that you have a preheating tank that turns on and preheats water during times of excess solar production, and then a secondary tank for your hot water that runs off your batteries to make sure that you have all the hot water when you need it. So doing more comprehensive building design measures is a new kind of opportunity. SMA has just announced SCADA controlling for their inverters. So for commercial air conditioning systems that are also SCADA controlled, you can start integrating your battery bank and your solar array and your more heavy duty electrical appliances so that they'll only run during times of excess solar production, and that can reduce the size of your battery bank. These codes, the only one thing to watch out for is just make sure that your electric service is matching your inverter, because the inverters are custom made for each electric service. One item of debate that we didn't do on our off-grid project, but it was kind of a consideration, was, should we consider on off-grid more luxury-oriented homes, should we consider three-phase electric service rather than split-phase? What's easier on a battery bank, three-phase service versus split-phase service? three-phase, you have more what they call momentum in the system. So I suspect that three-phase is a smoother power draw out of the battery than 240 split phase, but I'm not sure on that. Now, there's a lot of unknowns in this industry. We talked about disconnect locations. Everything that can be connected to that power distribution panel between the meter and your load are energy management devices, batteries, solar arrays, wind turbines. Anything that has to do with your building energy management can be located between your point of interconnection and your main service panel. So we talked about EMT tubing versus flex metal tubing. Your lithium ion batteries need to be listed. So you're not allowed to take a lithium ion battery out of a wrecked electric vehicle and use it as a stationary battery for solar interconnection. So it's not that you don't have hobbyists out there doing that, but as a business model, it's not allowed. Let's see, we cover these in more detail in our code class. There's one more point I want to get before we get to the end of it. Here we go. For in code, battery chemistries with corrosive electrolytes. The structure that supports the battery shall be resistant to corrosion. Metallic structure shall be provided with a non-conductive support members. Paint alone shall not be considered an insulating material. So it's just common to build your battery rack out of metal and then set the batteries on it. You really need to put an insulating material between your batteries and your metal battery rack if you're building your battery rack out of metal. This was kind of interesting. Batteries need to be in a vented room, but actually ASHRAE defines an air-conditioned room as a vented room. So putting your batteries in an air-conditioned space meets your ventilation requirements. And then you need to protect your batteries against accidental contact. There's more harsh constraints when you get into commercial systems. And so finally, kind of the last point that this is kind of for the dreamers out there, where you have your building electric use. And of course, this is in kilowatts, and this is in time or hours. And so we see it, if this is our load profile, the volume under the curve, and we've seen how a solar array can, turn on during the middle of the day and reduce that load. And then a battery bank can come on and provide us with some additional load leveling, but then you get into diminishing returns the further down this curve you go. The next, and maybe we can do some additional load shifting to put some of this into here to get that demand management down even a little bit further. But eventually, even all we're doing is smoothing out our building performance, but you're always going to be left with these valleys. Let me get a different ink color of empty space between your new building demand level and just your, even the difference between during the week and the weekend, where you're more at your base load during the weekend and at your weekday base during the week. You still have these valleys to go in. And when you think about it, what these valleys represent is if you're on a demand-based rate structure where maybe over half of your bill is kilowatt hours and the other half is based on kWh, Basically what these valleys represent is dirt cheap electricity, where if you, and what we see utilities, they may be going, instead of being a kilowatt hour rate structure based on volume under the curb or a demand rate structure based off the amplitude, they're trending towards more block based rate structures where it's you stay within this block of kilowatt hour and kilowatt parameters, and if you exceed the block you get into a higher rate tier. And so the optimal building demand profile is not one that is spiky or undulating. The optimal building demand profile is a perfect rectangle. And so how do we create a perfect rectangle of building demand? Well, with solar plus batteries, we're shaving off the top, but we still will have this undulating margin that reflects the difference between our base load and what our building can actually load level, that point at which demand management approaches diminishing returns. And so what do we do with that gap? Well, the answer is you increase your building usage, because this time frame in these valleys, that is dirt cheap electricity, and increasing your building energy usage during that time doesn't do anything to impact your demand charges. And so on the spikes where your demand is high, you use solar and you use batteries to take away from that. The answer on how do you fill in these batteries, you can Bitcoin mine. And so Bitcoin mining is a way to convert electricity into digital currency, and it funds the basis of Bitcoin, which is that crazy online currency that's trendy nowadays. Well, Bitcoin mining, the only way it's cost effective is if you have access to dirt cheap electricity. And this valley is exactly dirt cheap electricity. And so kind of the optimal building, if you really want to make your building demand management to be perfectly controlled between Bitcoin mining, battery management, and solar management, it's possible to have a perfectly flat load profile now. And that's kind of interesting because, your utility, they don't want you decreasing your electric use, but they do want you increasing your electric use. And so so no matter how they divide up their rate structures, even if they go into a perfectly, block-based rate structure, there's always going to be opportunity for the building designer to figure out how can we make our building use a perfect rectangle. And so after you do solar, after you do batteries, after you do load shifting, I would say look towards Bitcoin mining as the next step in your facility energy management if you're really looking out towards kind of future trends. So with that, we're at the end of our program. My email address is jrskromer@gmail.com. You're always welcome to email me with any questions. I want to make sure you get the information that you came for. Now, I do run a website called community.solar where I will report lessons learned from the projects that I'm working on, and also do audience follow-up questions. So if you want to, just visit my website and create a profile or ask a question in the chat box. That's the best way to get in touch with me after class, is to go ahead and do that. And with that, thank you for coming, and I'll pass it back to Half Moon.
Thank you, Mr. Cromer. If you need continuing education credit for this webinar, please remember to take the quiz after the webinar ends. If you don't have time to take the quiz or it doesn't appear for you, you can always access it via the follow-up or thank you email that is sent about 1 hour after the webinar has ended. Certificates will be emailed in PDF form. And if you have any remaining questions, you can reply to any of the emails received regarding these seminars or call into our office. Thank you again, Mr. Cromer, for the presentations, and thank you to everyone in attendance. Here's your quiz.